Hey everyone, and welcome to our seventh numerical analysis video. Today we're going to talk about numerical integration, and we're going to spend a few videos talking about numerical integration. Let's do a review of how it is that we began our study of how to compute the integral of f of x from x equal a to x equal b. Remember what we did? First, we decided we'd approximate this integral. And to do that, we partitioned the interval from a to b into n subintervals of equal length. And each of those subintervals had length delta x. So let's see what this might have looked like. We have a continuous function, f of x. That doesn't look like f of x, does it? Oh well. And we want to compute the integral of f of x from a to b on the x-axis. And if the graph lies above the x-axis, then the definite integral is equal to the area bounded by the graph of f of x and the x-axis. So the integral of f of x from x equal a to x equal b is the area of this region. And realizing that that was the case, we got this bright idea. First of all, we partition the interval AB into n subintervals of equal length. Delta x equals b minus a over n. So we have n subintervals here. Okay, use your imagination. There are n of them here, a lot of them here. And for I equal 1 to n, we pick a point in the I subinterval, and we call it x of I. So here's the I subinterval. We picked a point, we call it x of I. Here's the first subinterval. We pick a point, we call it x of 1. Here's the second subinterval. We pick a point, call it x of 2, so on and so forth. And in the nth subinterval, we pick a point and call it x of n. So in every subinterval, we pick a point completely at random. And if it's in the first subinterval, we call it x of 1. If it's in the second subinterval, we call it x of 2. If it's in the ith subinterval, we call it x of I. And then for I equal 1 to n, we construct a rectangle of width delta x over the ith subinterval. And maybe I should have mentioned that earlier. I did mention it, but I should have emphasized it. The width of this interval and the width of all other intervals is delta x. So point 3 says, for I equal 1 through n, in other words, over each subinterval, we'd construct a rectangle of width delta x such that the bottom of the rectangle rested on the x-axis. So here's the bottom of the ith rectangle. And such that the top of the rectangle passed through the point x sub I, f of x sub I. So here's our ith subinterval. It has width delta x, has to all of the subintervals. The bottom rests on the x-axis. The top goes through the point x sub I, f of x sub I. And we do that over each subinterval. So this rectangle, the first one goes through the point x sub 1, f of x sub 1. And the second rectangle goes through the point x sub 2, f of x sub 2, and so forth. And in the nth subinterval, the bottom of the rectangle rests on the x-axis. And the top of the rectangle goes through the point x sub n, f of x sub n. So we filled this region up with rectangles. And after we filled this region up with rectangles, we said, you know what? We're trying to compute the integral of f of x from x equal a to x equal b. And the integral of f of x from x equal a to x equal b is just the area bounded by the graph of f of x and the x-axis from x equal a to x equal b. And we said, you know what? These rectangles, when we stack them together side by side, form a region whose area and shape is approximately the same as the area and shape of the region bounded by this graph of f of x and the x-axis between x equal a and x equal b. And we said to ourselves, you know what? If we add up the areas of these rectangles, that will be approximately the same as the area bounded by the graph and the x-axis, which also happens to be the same as the integral of f of x. So to approximate the integral of f of x from x equal a to x equal b, we just decided we'd add these rectangles together, the areas of the rectangles. And we said integral from a to b of f of x is approximately equal to the area of the first rectangle plus the area of the second rectangle, dot, 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 plus the area of the ith rectangle, dot, 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 plus the area of the nth rectangle, And we said, you know something else? The area of the ith rectangle gives us a model that helps us to compute the area of all of the other rectangles too. The area of the ith rectangle is equal to the height. And let's see, what's the height of this rectangle? We go from x equals 0. We go from y equals 0 to y equal f of x sub I. The height of this rectangle is just the difference of the y coordinates. And on this line, y is 0. So the height of this rectangle is f of x sub I minus 0, or just f of x sub I. That's the height of the ith rectangle. And the width of every rectangle is the same. It's delta x. So the area of the ith rectangle is f of x sub I times delta x, height times width. And this serves as a model for how we compute the rest of the areas of the rectangles. For example, a sub 1 is f of x sub 1 delta x. A sub 2, f of x sub 2 times delta x. And a sub n is f of x sub n delta x. And so this gives us an idea of how we can approximate the definite integral. The definite integral is equal to the area of the first rectangle, f of x sub 1 delta x, plus the area of the second rectangle, f of x sub 2 delta x, plus the area of the ith rectangle, f of x sub I delta x, plus the area of the nth rectangle, f of x sub n delta x. And we said, you know what? There's a common factor in each of these terms, delta x. We can factor that out. So we have f of x sub 1 plus f of x sub 2 plus f of x sub I plus f of x sub n, whole thing times delta x. And then we looked at this and we said, you know what? The only thing that changes from one term to another is the subscript of x. And the subscript starts at I equal 1, and in increments of 1, it goes all the way to n. So we know what that is. That's the sum from I equal 1 to n of f of x sub I. And now we have an approximation for the definite integral of f of x, and it's written in summation form. And you know, maybe I didn't really have to do this last step. Tell you what, just forget I said anything about that. But this is what the definite integral is approximately equal to. The summand is just the area of the ith rectangle. Now there's a problem. This is only an approximation. And the reason it's only an approximation is that, well, this first rectangle is excluding area, this area right here, that should be included as part of the definite integral. This second rectangle is excluding area right here that should be part of the definite integral. And this same rectangle is including area that shouldn't be part of the definite integral, and so forth and so on. And we see that the problem is caused by the fact that the tops of the rectangles don't conform precisely to the contour of the curve, which is why we leave out area sometimes, and other places we include area that we shouldn't. So this is just an approximation. And we figured out, you know what? If we made these rectangles thinner, if we made the rectangles thinner, the tops of the rectangles would conform more precisely to the contour of the curve. And so we said this. To get a better approximation, make the rectangles thinner. And that's the same thing as saying make delta x smaller. And then we said, oh, that's good. How can we get an even better approximation? And we said, why not make delta x even smaller? It worked once, it ought to work again. And so to get an even better approximation, we make delta x even smaller. And we said, this is good, but we want the best approximation. We make as delta x as small as we can, or that's what we think. We could make delta x equal to 0, but ooh, you know what? We'd have a rectangle of height f of x of I and width 0. If we make delta x 0, we got a bunch of rectangles here that have width 0. That's not going to work. Huh. Okay. Well, we still want to make delta x as small as we can, but we can't make it equal to 0. And we realized, aha, we want to make delta x as small as possible without it becoming 0. In other words, we want delta x to get as close to 0 as possible without actually becoming equal to 0. And at that point we said, where have we heard that before? We're talking about a limit. Compute the limit as delta x goes to 0. And we have the definite integral of f of x from a to b equal to the limit as delta x goes to 0 And this thing, we might recognize this thing as being a Riemann sum of order n. So we let delta x go to 0. And we wonder what happens to that n. Well, n is the number of rectangles. So as the width of the rectangles goes to 0, the number of rectangles goes to infinity. Son of a gun. And of course, these two things are related. Delta x is b minus a over n. So as n goes to infinity, delta x automatically goes to 0. Now this gives us an idea of how we can compute definite integrals numerically. Just make one of these Riemann sums and make delta x smaller and smaller, and make n correspondingly larger. Now we can't let delta x, we can't do successive approximations and just say, we'll quit when two successive approximations differ by such and such. And again, the problem is that as we let delta x get smaller, we're going to gain accuracy by letting delta x get smaller. But as delta x gets smaller, we just have a cajillion calculations here, and the round-off error explodes. There is an optimal value of delta x. It might be 0.01 or 0.001. If we let delta x get smaller than that, the approximations actually end up getting worse because of round-off error. Now, there are a few things that we can do to sort of nip this in the bud. Let's look at some of them. Our definite integral, we're going to approximate by computing a Riemann sum of order n, and then letting delta x go to 0. And as delta x goes to 0, n is going to go to infinity. So maybe what we need to do is rewrite everything totally in terms of delta x, or totally in terms of n. I'm going to opt for writing in terms of n. B minus a over n is our delta x. So now we have everything in terms of n. And there are some questions here that I haven't answered yet. I'm going to need to face up to them. Notice what happens if I expand this Riemann sum. Every term here has a factor of b minus a over n, which means for each of these terms, we're going to have to compute b minus a, that's one operation. Then we're going to have to divide by n, that's another operation. Then we're going to have to multiply this thing by b minus a over n. So let's say that we let n equal 400 or 500. 500 times 3 operations here, that's 1,500 operations. Maybe what we could do is cut down the number of operations by doing this. oh, we have a common factor here. Let's put it on the outside of the parentheses. Now you see that? I'm just going to add all of this stuff together and then multiply by b minus a over n. So let's see, b minus a, that's one operation. B minus a divided by n, that's another operation. And this whole thing times b minus a over n, that's three operations. As opposed to, what did I say, 1,500 operations if we do it this way. We just saved ourselves a lot of round-off error by doing this. Now, there's something else that we need to resolve. When we first set up this model, I said x of 1, any point in the first subinterval. X of 2, any point in the second subinterval. Well, if we have our computer simulate this, we're going to have a criterion for deciding how x sub I is chosen in each subinterval. And the most common options are, we can have x sub I be the left endpoint of the subinterval. So x sub I is the left endpoint of the subinterval. X sub I is the right endpoint of the subinterval. Or x sub I is the midpoint of the subinterval. Those seem to be the three best options. We don't seem to stand to gain much by having a more sophisticated scheme. So let's pause here. This is our approximation scheme for the integral of f of x from a to b. Let's just see how we might tell our computer how to choose x sub I for each subinterval. How do we define our x sub i's? Let's say that x sub I is the left endpoint of the ith subinterval. So x sub 1 will be the left endpoint of the first subinterval. In other words, x sub 1 will be the same as a. So x sub 1 is a. X sub 2 will be the left endpoint of the second subinterval. And x sub 2 is the distance of delta x from a. So x sub 2 is a plus delta x, or a plus 1 delta x. X sub 3 is the left endpoint of the third subinterval, and x sub 3 is a distance of 1 delta x, 2 delta x. X3 is a distance of 2 delta x from a. So x sub 3 is a plus 2 delta x. X sub I is the left endpoint of the ith subinterval. And let's see, how does this go? X sub 1 is a plus 0 delta x. X sub 2 is a plus 1 delta x. X sub 3 is a plus 2 delta x. X sub I is a plus I minus 1 delta x. And so x of n would be a plus n minus 1 delta x. This is how we would define our x of i's if we let x of I be the left endpoint. What if we let x of I be the midpoint of each subinterval? Okay, what about our midpoint? Here x of 1 is the midpoint of the first subinterval. X of 2 is the midpoint of the second subinterval, and so on. And these intervals each have a width of delta x. If we start at A and go half the length of this subinterval, we get to x of 1. So x of 1 is A plus 1/2 delta x. From A to x of 2, we go a distance of delta x plus 1/2. Now, how would I write that? A plus 1.5 delta x. Maybe I should write this as 0.5 delta x. And x of 3, we go delta x, 1/2 delta x. X of 2 equals A plus 2.5 delta x. X of 3, I'm sorry. X of I think I see where this is going. 2 is 1 less than 3, 1 is 1 less than 2, 0 is 1 less than 1. So x of I is A plus I minus 1.5 delta x. And x of n, A plus n minus 1.5 delta x. I'm saying here that n minus 1 should be the digit to the left of the decimal point here. This is one number, n minus 1.5. This is one number, I minus 1.5. I minus 1 is the decimal point, is the digit to the left of the decimal point here, and so forth. And now we'll do the right end point. Okay, right end point. Right end point in the first subinterval, x of 1 is at the right end point. We start at A and go a distance of delta x. So this would be x of 1, this would be A plus delta x. To get to x of 2, we start at A and go 2 delta x. So x of 2 is A plus 2 delta x, and so forth. Now, there is an alternate way of cranking these things out. What I recommend, for example, is if we have the right end point being x of I, just say x of I equals A plus 1 star delta x. X of 2 equals A plus 2 star delta x. And we do that in some kind of a loop. Each time we go through the loop, we compute x of I for the next loop. What we can do as an alternative is to get x of 2, just add delta x to x of 1. So in other words, have the same x value each time and just increment the x value by delta x each time through the loop. I'm not sure if I like that way as much as I like this way, and I'll tell you why. Delta x will be a small number, maybe a crude approximation. And if we keep adding delta x to our former x value, I think the round off error is going to build up. What I would say is compute each of these by taking a and adding to it some multiple of delta x. So to approximate the definite integral, we add up the sums of our f of x of i's. And then to cut down on operations, we multiply by delta x at the end. And we just do this once. We let n be such that delta x is approximately the optimum value. And I guess that depends on what precision the variables are and so forth. But we'll probably use 0.001 or something like that. Now, this gets us a good approximation, but we're still going to have the problem that if this is our graph, our rectangles are still going to be doing that. So we're still going to have error, but if our rectangles are thin, this error is going to be small. Even so, we'd like to cut this error significantly if we can. And that's what we're going to talk about in the next lecture.